Asymptotic notations. The concept of efficiency in algorithms pertains to how effectively they utilize resources such as time and storage. It is evident that an algorithm's performance can differ depending on the type of input it receives. As the input size grows, the algorithm's behavior might undergo significant changes. The asymptotic analysis deals with studying how an algorithm's performance alters as the input size becomes exceptionally large. It enables us to grasp the algorithm's behavior under these conditions and constitutes a fundamental principle in algorithm analysis. Asymptotic notations are mathematical tools used to express the running time of an algorithm as the input approaches a specific or limiting value. In essence, they aid in comprehending how an algorithm's running time changes concerning the input size. Let's take the example of bubble sort. When the input array is already sorted, the algorithm exhibits linear time, representing the best-case scenario. Conversely, when the input array is in reverse order, it demonstrates quadratic time, representing the worst-case scenario. For situations where the input array is neither sorted nor in reverse order, the algorithm takes an average amount of time. Asymptotic notations are employed to symbolize and convey these different scenarios. The three main asymptotic notations. Big O notation. It characterizes the upper bound of an algorithm's running time, providing us with the worst-case complexity. Omega notation. It denotes the lower bound of the running time, revealing the best-case complexity of the algorithm. Theta notation. This notation bounds the function from above and below, encompassing both the upper and lower bounds of the running time. It is well suited for analyzing the average case complexity of an algorithm. Big O notation. Big O notation provides us with an upper bound on the running time of an algorithm. It guarantees that the algorithm's performance will not exceed a certain level, even for large inputs. As a result, Big O notation is particularly valuable for analyzing the worst-case scenario of an algorithm. It allows us to understand how the algorithm behaves when faced with the most challenging input instances. The expression above can be defined as follows. The function f of n belongs to the set big O of g of n if there exists a positive constant c such that function f of n lies between 0 and cg of n for sufficiently large n. Omega notation. Omega notation offers a lower bound on the running time of an algorithm. It guarantees that the algorithm's performance will be at least as good as the specified bound, even for large inputs. Omega notation is particularly useful for analyzing an algorithm's best-case scenario. By using omega notation, we can determine the minimum amount of time an algorithm will take to complete its task under favorable conditions. The given expression defines that a function f of n belongs to the set omega of g of n if there exists a positive constant c, such that it remains greater than cg of n for sufficiently large values of n. Theta notation. It encloses the function from above and below. It represents both the upper and lower bounds of the running time. As a result, it is perfect for analyzing the average case complexity of an algorithm when the performance can vary depending on the input. The above expression can be described as a function f of n belongs to the set theta of g of n if there exist positive constants c1 and c2 such that it can be sandwiched between c1 of g of n and c2 of g of n for sufficiently large n. If a function f of n lies anywhere in between c1 of g of n and c1 of g of n for all n is greater than or equal to n sub 0, then function f of n is said to be asymptotically type-bound.